Hello everyone, welcome to the YouTube channel of Yourpedia Engineering Career Point. So I am Vinesh Sharma, your mentor of mechanical engineering. So as you know, the BEL has announced the date of the upcoming exam here, that is on 31st of May. And for that purpose, we have already launched our module here, which is basically specifically for the last 20 days here. Okay, and if you see, in the last 20 days, you have to do a lot of practice here because the revision is very important for you, and the practice of all the previous year questions as well as all the important questions are very crucial for you. Okay, so for that purpose we are providing you this particular module here, and this module we are providing you a lot of PDFs here. First of all, we are providing you the online test series. Along with that, we are providing you the practice question PDFs here for each subject, which is comprising of 150 questions. Along with that, we are conducting the live classes in which you are going to cover each and every subjects here. Okay, so I hope you are very well prepared with this particular exam here. Okay, so in this particular video, this particular video is basically a demo lecture for which I basically am covering up in the live session here. Okay, and in this particular video I am going to cover up the vibration part, which is basically a very important topic. And from this particular portion, this is basically a part of a theory of machine. Okay, and from this particular portion here, a large number of questions are already asked in the previous year also. Okay, so just making sure that you cover up this portion very well. Okay, because this portion is very simple, although it seems like that it is a very difficult portion, but it is not like that. The numericals, the theoretical questions which is asked from this particular topic is very simple. If you have a clarity of each and every part, if each and every topic, then you will be able to crack these questions very easily. Okay, so before any delay, so let us start our session here. So in this case, first of all, we are going to analyze our vibration analysis. Now, what is the meaning of vibrations? First of all, the vibration is basically a to and fro motion of a body about its mean position. Okay, and we have different types of vibrations here. So as you know, we have a vibration, we have a transverse vibration here, we have a longitudinal vibration here, and as well as we have a torsional vibration. We have a torsional vibration here. So these are the three general types of vibration which we have to cover up in this particular chapter. And out of these three vibrations, for the most important one is the longitudinal vibration, because whenever you are covering this particular chapter, you have to cover up the different cases. Like we have to cover up the case of undamped vibration. Along with that, we have to cover up the damped vibration with force and without force consideration here. Okay, so all of these analysis we are going to do on the longitudinal vibrations only. Understood? So let us start here with the first question. So if you see in the first question, we can see in a damped vibration system, the damping force is proportional to the. First of all, just see what is the meaning of damped vibration system. So if we talk about the simple vibration system, so simple vibration system consists of three elements here. First one is the mass, then we have a simple damper, and then we have a spring. Okay, these are the three elements which comprises of the which basically cover up in the vibration system here. So now, whenever you are studying the vibration chapter, there are different cases. There are different types of vibrations here. We are going to see the free vibration here. Okay, in case of free vibration, actually you are not applying any external force over the system here. So let us suppose if I am showing you the vibrating system like this one. Okay, so here we have a simple spring, and here we have a mass m, and spring is having a stiffness k here. So in that case, you will see along with spring we have a damper. So you can understand the damper in this way. The damper is basically it is a resistance here. It is helping you to dissipate the vibrations which are basically induced in the body. Understood? So this is a simple vibrating system in which we have a mass, we have a spring, and we have a damper. And here C is representing the damping coefficient of this particular damper here. Now in this case, if you apply the force over the system at time t equal to 0, and after providing some disturbance into the system, if you just remove all the forces and the system is vibrating on its own, then we say it is a case of a free vibration here. Okay, so in the case of free vibration, we doesn't apply any force over the system. We just apply the force only at the initial stage, okay, to disturb the system here. Now then we have simply a force vibration case. In the case of a force vibration, what you are doing, you are actually applying the force continuously over the system here. For example, let us say there is a vehicle which is on which is basically switched on here, and it is turning on the traffic lights here. Okay, so in that case, the system will continuously vibrate here. Why it is vibrating? Because there is unbalanced force which is acting over the vehicle, I can say. Okay, so in this case of a force vibration system, you are going to see the same vibrating model is going to be there. That is, we have a spring, we have a damper, along with that we have a mass. But now in this case, what is happening? In this case, the mass is continuously acting upon a force. Okay, let us say F here. Now in this case, in these two cases, we have to cover up the damped vibration case as well as we have to cover up the undamped vibration case here. So this comprises of the damped vibrations here, and this comprises a case of the undamped vibration here. Now what is the meaning of a damped and undamped? So let us suppose, just see here, I have told you that we have three elemental elements here, the mass, spring and damper. So let us suppose if there is no damper. Okay, if there is no damper, so I can say the system is continuously going to be vibrate, okay, and the vibration are not going to be dissipated here. Okay, in that case the vibrations are not going to be dissipated. So we can say it is a case of a undamped system. But now let us say if the friction is present around the vibrating system, then it is a case of a damped vibration here. And generally the atmospheric air is present all around the bodies here. So I can say the air is acting as a damper for all the cases. Okay, so practically you are going to see we have a damped vibration cases here. So damped vibration can be free vibration here, and it can be a force vibration case here. Okay, so that's a very simple case. Now in this question, what is asked? In a damped vibration system, okay, in a damped vibration system, damping force is proportional to. So now just see, if you are apply the force in this case, so let us say if I take if I consider the free vibration case, okay, and if I create a free body diagram of a mass here, you are going to see what you have done. You have just displaced the mass by some distance due to this external force. Now if you have removed the force, what will happen? First of all, the spring will try to bring back this mass to its mean position. Okay, and correspondingly the spring force is given by K into X here. Okay, or stiffness multiplied by the displacement of the spring force, and correspondingly it is acted upon by the damping force also. And in this case, the damping force is given by the damping coefficient multiplied by the velocity here. Okay, so in this case, actually if you see, the damping force is nothing but it is equal to C multiplied by X dot. Okay, and here we assume that when the system speed is very low, in that case the damping force is directly proportional to the velocity here. But let us suppose if the velocity is very high, okay, if the body is vibrating with a very high speed, in that case the damping force is going to be vary with the square of velocity. Understood? So just ignore that part, because in practical scenario we always encounter with the low vibration speed cases here. So I can say damping force is proportional to the velocity here. So option number C will be the correct answer of this particular question. Now we have our next question, where when there is a reduction in the amplitude of vibration over every cycle of vibration, then body is said to have. Okay, now just see in this case what happens here. So let us suppose we have a simple, again, spring mass system is there, and here I have installed a spring which is having a stiffness of K, and it is also, there is also a damper present here with a damping coefficient C here. Okay, now the mass of the body is represented by M here. Now what I am doing, I am just applying a external force F at time t equal to 0. Okay, only at the initial condition I am applying a force just to disturb the system here. So let us say the mass has been displaced by some distance. I am assuming it has been displaced by distance x here, and a new position of the mass is M. And now if I remove the force, what will happen? The mass will be acted upon by the spring force, it will be acted upon by the damping force. Along with that, you have to apply the inertial force also over it. So if you see, the differential equation of this particular case will become mass into acceleration. Okay, this is the inertia force plus damping force plus spring force. It has to be equal to 0. Why we are introducing the inertial force here? Because to make the dynamic state body into the statistical equilibrium case here. Okay, so in order to convert the dynamic body into a case of statistical equilibrium case, what we have done, we have making sure that inertial force is being added up so that the net force acting on the body is equal to 0. Okay, now in this case, if you see, if we solve this entire equation, okay, we have different type of system there. Okay, like we have a over dam system, then we have a critical dam system, and then we have a under dam system. Okay, so now I am not going into so much detail because I will cover that in the subsequent questions here. So now let's see. If I plot a graph between the displacement with respect to time, if I plot a graph between the displacement with respect to the time here, so here you can see initially the body has been displaced by, let us say, displacement with the distance of x naught. Okay, in that case it will be vibrate like this one here. Okay, so here you can see the maximum amplitude of the body is x naught. Maximum amplitude of the body is x naught here. Okay, so this is our first cycle. This is our first cycle. Now after that what will happen? After that what will happen? Due to the damper present inside the system, it will offer some resistance to the vibration here. Okay, it will dissipate, it will try to dissipate the energy here. So due to which what will happen here, the amplitude of the vibration will get reduced like in this way. Then further, after the completion of cycle, it will further decrease. Okay, so if in this case you are going to see the amplitude is continuously decreasing over the period of time, and after some period of time this amplitude will become 0. So I can say the vibration will be diminished here. Okay, so here I can say this is our amplitude now, this is x1. So here you can see. Okay, so here you can see the cycle has been started from point number 1, the next cycle has been started from point number 2, and the third cycle has been started from point number 3 here, and similarly the fourth cycle has been started from point number 4. So subsequently, if you see, the amplitude of the vibrations are decreasing here. Why it is decreasing here? Due to the presence of the damper inside the system. So in that case the vibration is known as the damped vibration. Okay, just remember that in that case the vibration is considered as a damped vibration here. Okay, so option number C will be the correct answer in this case. So that's a very that's again a very simple case. Okay, that's again a very simple case here. Now the next question is so now the next question is for a critical damping factor will be, for a critical damping factor will be. So now just see in this case what is the meaning of damping factor. Now let us do some mathematical derivation of the, let us study the mathematical portion of the free damped vibration here. So again here we have a spring of stiffness K, here we have a damper with damping coefficient C, and here we have a mass of body, a mass of a body which is represented by m here. Okay, so in that case if I write down the value of the governing differential equation, it will be written as mx double dot plus cx dot plus k into x equal to 0. Okay, actually the question from the vibration part is very simple. The only thing which is required is required the revision part. Okay, so that is why I am suggesting you that just practice as much as questions possible here in the last 20 days. If you are able to solve a very large number of questions there, then it will be sufficient for your particular exam this. Okay, of this particular exam here, because in this exam you are not going to see very difficult numericals is being asked. Okay, only the simple theoretical question is going to be asked in this particular exam here. So now in this case if you see, if I just simplify it further, I can rewrite this differential equation in this way: x double dot plus cm x dot plus k by m multiply by x equal to 0. Okay, now I can rewrite this equation in the form of zeta here. So it will become something like that here. So here you can see, if I just compare the equation number A and equation number B, you are going to observe that 2 zeta omega n is equal to C by m here. Okay, it will come equal to 2 zeta omega n will become equal to C by m. Now in this case actually what happens here, this zeta parameter is known as the damping factor. This zeta parameter is known as the damping factor here. It is known as the damping factor, it is known as the degree damping ratio here. Understood? Now just see, if I just put, if the value of the zeta is equal to 1, if the value of the zeta is equal to 1, in that case the equation will simplify to 2 omega n equal to C by m here. Okay, so now you can see what I have done. I have just put it down the value of the zeta equal to 1. In that case, the equation gets simplified to 2 omega n equal to c by m here. So in that case, this damping coefficient, okay, when the value of zeta is equal to 1, this particular damping coefficient is known as the critical damping coefficient here. It is known as the critical damping coefficient here. Okay, so in that case, now the question arises, critical damping coefficient, how do we define the damping factor or a damping ratio here? So actually the damping ratio is nothing, it is a ratio of the damping coefficient to the critical damping coefficient here. Okay, it is known as the ratio of the damping coefficient to the critical damping coefficient here. And what is critical damping coefficient? The value of the damping coefficient when the value of zeta, that is damping factor, is equal to 1 here. Understood? So in this case I can say this zeta. Okay, so now just see, on the basis of the value of the zeta we define a different type of systems here. Okay, so let us say if the value of the zeta is less than 1, in that case we say the vibrating system is known as the underdamped system. We have a underdamped system here. And similarly, if the value of zeta is equal to 1, in that case we say it is a critically damped system here. Critically damped system here. Okay, just remember that part. And in the same way, if the value of zeta is more than 1, then we say it is a overdamped system. Overdamped system here. So I can say the option number for a critical damping, the damping factor will be zeta is equal to 1 here. Okay, just remember that part, because for the critical damping, for a critically damped system, the value of zeta is going to be 1, and corresponding to that the damping coefficient is known as the critical damping coefficient here. Okay, and remember one more thing, critically damped system and the overdamped system does not considered as the vibrating system here. Why not? Because in this case, if you see the graphical variation or graphical representation of the displacement with respect to the time, there is no to and fro motion of the body. Okay, but in the case of an underdamped system, we have a to and fro motion of a body about its mean position. And for a system to be called as a vibrating system, that is a required condition that the body have to have a to and fro motion about its mean position here. Okay, so just remember that these systems are not considered as the vibrating system. These are not considered as the vibrating system. Okay, just remember that part. That is very important for you. You have to to check those, you have to just see the graphical representation of the displacement versus time, or either you can go through the mathematical solutions of this particular systems here. Okay, now the next question, a mass of 1 kg is attached to the end of the spring with a stiffness 0.7 Newton per millimeter. Now the critical damping coefficient, of the system. What is the meaning of critical damping coefficient? Critical damping coefficient means the damping factor value has to be equal to 1. Okay, corresponding to one value of the damping factor, the value of the damping coefficient is known as the critically damping coefficient here. Okay, so here we have a system like this one. So here you can see, so in this case the stiffness is equal to 0.7 Newton per millimeter, or I can say it is equal to 700 Newton per meter here, and correspondingly the mass is given to you as 1 kg here. Okay, so in that case, what is the formula of the critical damping coefficient? So just right now I have told you that we have a governing differential equation. So governing differential equation is written as this way. In this way you can write the governing differential equation. This is x double dot plus c by m multiplied by k by m, x equal to 0, or you can write x double dot plus 2 zeta omega n x double dot plus omega n square x equal to 0. Okay, so in that case, if you compare these two equations, you will find the c by m is equal to 2 zeta omega n, and when zeta is equal to 1, in that case damping coefficient is known as the critical damping coefficient. Okay, I can directly write Cc upon m is equal to 2 omega n. Okay, and what is the value of the omega n? Omega n is defined as the natural frequency of the system, which is basically depending upon stiffness and mass here. Okay, so natural frequency is having a formula of under root of k by m. So after simplification, I can write the Cc, the critical damping coefficient, is going to have a value of 2 under root of k into m here. So that is the formula of the critical damping coefficient. So you can see, so in that case, the stiffness is given to you as 700, the mass is given to you as 1 here. Okay, and if you just solve it, you will get your final answer, and the answer you are getting in this case, it is coming out to be around 52.92 Newton second per meter here. So option number C will be the correct answer. Just solve it and you will get your final answer, this one. Okay, now the next question. A block whose mass is equal to 4 kg is fastened to a spring with a spring constant K is equal to 64 Newton per meter. The block is pulled from its equilibrium position on a frictionless surface and released. The period of the resulting motion in this second is. What is the meaning of period? What is the meaning of period here? So let us suppose, just understand, there are some few terms like frequency, period, okay, natural frequency, damped frequency. You should be aware of that. You should be aware of the meaning of these terms here. Okay, just right now I have shown you the graph of the displacement with respect to the time, and it is drawn something like that here. Okay, this is how you draw the graph. Now in this case, you can see that the cycle has been started from point number A, and at point number 1 the cycle has been completed. The one cycle has been completed. Basically, the time required to complete this cycle is known as the period. Okay, so let us suppose this cycle is completing in 5 seconds, then the period is 5 seconds. If the cycle is completed in 2 seconds, then the period is 2 seconds. Okay, and what is the meaning of frequency? There is one term that is time period, and there is another term which is frequency. So here you can see what is the meaning of time period. The time required to complete the cycle. How much time has been taken to cover up this entire this much amount of displacement here? That is known as the time period. Okay, what is the meaning of frequency? How many cycles are being covered in 1 second? That is the frequency. How many cycles are being covered in 1 second? So let us suppose this cycle is completing in, let us say, 0.1 second. This displacement, okay, this cycle is taking 0.1 second. So I can say the time period is 0.1 second. Now if I ask you that how many cycles are being how many cycles are being finished in 1 second here? So you can say, sir, one cycle is taking a time of 0.1 second. So I can say 1 upon 0.1 cycle are covering in the 1 second here. So that simply means the 10 cycles are being covered in the 1 second here. So I can say the frequency is going to be equal to 10 only. Understood? That is having a unit of hertz, basically 1 by a second. Okay, just remember that part. So in this case, if you say what is being asked to you, it is given that the body has been displaced from its mean position. Let us say it is a mean position. Now the body has been displaced from its mean position, let us say up to x1, and then it is released. Now there is no damper in this system. You can see the diagram. Okay, so I can say the body, after reaching the x1 position, it will move in the backward position toward left here, and it will reach at position number x2 here. Okay, so in this case, the mass of the the weight of the body is acting downward. The weight is acting downward, so there is no role of weight. Okay, so now you can see the motion of the body in the horizontal direction is entirely due to the spring force only, because you are just applying the force to disturb the system here. After that, you are removing this force. I can say in this case the omega n is nothing. It is directly a ratio of under root of k by m. Natural frequency is going to be equal to under root of k by m here. Okay, so if you just put all the values here, 64 divided by 4, you are going to get 16 kg, and the natural frequency system will come out to be as 4 radian per second here. 4 radian per second here. Now just remember the formula. Omega n is basically known as is equal to 2 pi f here. Okay, f is also having a this omega n is also is called as a natural frequency. This f is also called as a natural frequency. The only difference is in the units here. Omega n is having a unit of radian per second. Okay, f is having a unit of hertz here, that is 1 by second. Understood? So I can say the frequency is going to be equal to 4 radian divided by 2 pi. And what is the relationship between the linear frequency and the time period? Just right now I have told you the time period is nothing but it is equal to inverse of the frequency. So I can say the time period will be 2 pi by 4, it will be equal to pi by 2 second. That means the cycle is going to be completed in pi by 2 second here. Okay, so that will be the answer here. So option number B is going to be the correct answer. Now let's move to our next part. In free vibration, the velocity vector leads the displacement vector. So that's a very nice question here. So in order to solve this question, you have to understand first of all the differential equation of this free vibration without any damper. Okay, and you have to calculate the value of the solution. You have to find out the solution of the differential equation also. After that, you can find out the value of the velocity as well as the acceleration here. In the case of a free vibration, here I am assuming that there is no damper. So this is our system. This is our system. Okay, here we have a stiffness, here we have a mass. Now what I have done, I have just applied the force. In that case, you can see the mass is acted. So if I displace the mass in the downward direction and if I just remove the force, what will happen? The body will move in the upward direction. Why? Due to this spring force. So let us say spring force which is acting over the body is equal to kx. So you can see due to this unbalanced force, the system is continuously vibrating here. Okay. So in order to analyze this body under the equilibrium case, what we have to do, you have to use the D'Alembert principle. You have to add the inertial force over it. Okay. So if you add the inertial force, the the governing differential will become mx double dot plus kx equal to 0. That will be the governing differential equation. Okay. So in this case, you can see x double dot plus k by m x equal to 0, or I can write x double dot plus omega n square x equal to 0. So that will be a governing differential equation in this case. Okay, so if you just solve this equation, you will find the governing solution of this particular equation is given by capital X sine omega n t plus phi here. So that will be the solution, where small x is representing the displacement of the body at any particular period of time t, and correspondingly x is representing the amplitude, the maximum amplitude of the body at the initial time. Okay, so in that case, if I just create a displacement versus time graph, okay, the amplitude is going to be remain constant. Amplitude is not going to be decreased now because there is no damper, there is no friction, there is no system which is dissipating the vibration, which is basically eliminating the vibration here. Okay, so the amplitude is going to be remain constant. Just remember that part. Now if you want to calculate the value of the velocity, velocity is nothing but simply the rate of change of displacement. So I can write v is equal to x dot, or I can further write it as omega n x cos of omega n t plus phi here, which can further be written as omega n x sine of 90 plus omega n t plus phi here. Okay. Similarly, if I just calculate the value of the acceleration vector, just wait a minute. If I calculate the value of the acceleration here, it will be equal to dv by dt, or it can be written as double differentiation of x with respect to time here. So you are going to see the expression will become minus omega n square x sine omega n t plus phi here. Okay, which can further be written as omega n square x sine 180 plus omega n t plus phi here. So now you can see the velocity vector is basically leading the displacement vector by 90 degree, the acceleration vector leading the displacement vector by 180 degree. Okay. So in this question what is asked, the velocity vector lead the displacement vector by 90 degree. If they ask you that the acceleration vector leads the displacement vector, then it will be the 180 degree. And if they ask you that the acceleration vector lead the velocity vector, the answer will be again 90 degree. Understood? So option number D will be the correct answer here. So again that's a very simple question, by the way. Now the next question, an overdamped system vibrates with frequency more than natural frequency. So first of all, just see, in the case of overdamped system, the value of the damping factor is more than 1. Okay, in that case there is no vibration at all, because if you just solve out the if you just see the final solution of the damped vibration case, there is no trigonometric functions here. Okay, there is an exponential term, so that is why we say the system does not vibrate at all here. Okay, and if you create a graph between the displacement versus time, so graph will be shown something like that here. So this black color graph is representing the free vibration case. This black color curve is representing the free vibration case. In the case of free vibration, there is no damper, so I can say the value of zeta is equal to 0. Okay. Now in the case of underdamped system is a vibrating system in which the friction is there and the amplitude of the vibration is continuously decreasing. So I can say the graph is going to be plotted like in this way. Okay, so now you can see this red color graph is basically representing the underdamped system here. Okay, so this red color graph is having the value of zeta less than 1. But now if you consider the critically damped system, in the case of critically damped system, we have a zeta value equal to 1. What is the characteristics of critical damped system? If you see, in the case of a critical damped system, if you just leave the body, if you just remove the force here, the body does not vibrate at all about its mean position. This horizontal line is representing the mean position here. Mean position. Okay, this is a time axis. Now you can see the body is just coming out to its mean position in a very short period of time here. So this green color line is representing the zeta equal to 1 here. Just remember that part. And in the case of a overdamped system, we have zeta greater than 1. In the case of overdamped system, if the system is displaced by some distance and then the force is removed, the body will come into its mean position after a certain period of time, but it is not going to go below the mean position here. That simply means it is not vibrating at all. Okay, so this is how the displacement versus time graph is plotted for the critically damped, overdamped, underdamped as well as the free vibration case here. Okay, just remember the graph here, that is very important for you. Okay, so if you just see the practical example, the overdamped system is having a practical example of door closure. The critically damped system is having a practical example of a recoiling of a spring in a gun here. Okay. Now the next question, the number of cycles of motion completed in 1 second, it is known as. So just right now what I have told you, time period is basically the time required to complete one cycle, and frequency is basically the number of cycles completed in 1 second. So I can say it is nothing but it is the frequency here. So option number B will be the correct one. Next question, what is the degree of freedom in the context of kinematics? So that's a very simple question, although degree of freedom is having a different definition in different subjects here. In the theory of machine or in kinematics, we have a different meaning of I can say different meaning of the degree of freedom, and in the thermal portion we have a different meaning of the degree of freedom. So in the context of kinematics, we say it is representing the minimum number of variables required to fix the position of the machine here, okay, or to fix the position of a state of a configuration here. So I can say it is representing the minimum independent variable specified to fix the configuration here. So option number D will be the correct one. So for example, let us say if you have a 4-bar chain and the value of the degree of freedom is 1, that simply means only one input is required to fix all the state of the links here. Okay, to get a defined constraint output from the mechanism, you have to supply only one input. If the value of the degree of freedom is 0, sorry, it is 2, if let us say, that simply means you have to provide 2 inputs to get a defined, or I can say to get a constrained output from the system here. Okay, so option number D will be the correct one. Next question. Whirling speed of a shaft coincide with the natural frequency of the. Now what is the meaning of the whirling speed actually? See, whirling speed, whipping speed, and the critical speed. Critical speed. All of these are the same thing only. Critical speed of the shaft is that speed at which the shaft tends to vibrate violently in the transverse direction. So let us suppose if you have a shaft like this one, and this is the longitudinal axis. Now in this case, the center of gravity of the pulley or a shaft here, it is not coinciding with the, let us say we have a pulley installed here, and the center of gravity of the pulley is not coinciding with the longitudinal axis of the shaft here. In that case, what will happen? If the shaft is rotating at a very high speed, due to the some eccentricity, in that case the outward centrifugal force will act over the pulley here. Okay, so with the increase in speed, you are going to observe, with the increase in speed the centrifugal forces will increase. Okay, so that simply means at high speed the shaft try to wobbles about its mean position. Okay, and the whipping speed, whirling speed, critical speed, the speed at which the shaft vibrates in the transverse direction violently, that particular speed is known as the critical and whirling speed here. Okay, just remember that part. So basically it is coinciding with the natural frequency of the transverse vibration here. Transverse vibration simple means the vibration of the body is taking place perpendicular to the axis here. Okay, in the case of longitudinal axis, vibration are taking place parallel to the axis here. Okay, now the next question, question number 11. In a system for vibration isolation, if the frequency ratio means omega by omega n is greater than 0 and less than √2, then for all the values of the damping factor, the transmissibility will be. What is the meaning of transmissibility? Actually what happens here, see, whenever you are installing any machines over in a structure here or in a building here, okay, first of all you have to understand when the machine runs, there are some unbalanced forces which are coming into picture here. Okay, which is basically creating the vibration in the machine itself. Now the unbalanced force which are being produced in the machines are getting transmitted to the foundation here. Okay, or I can say to the structure or to the building here. So basically transmissibility is defined as the ratio of transmitted force to the foundation, okay, divided by the total unbalanced force which is producing the system here. So if you just simplify it further, you are going to have a transmissibility formula like this one here. So just remember the formula, only the formula is very important for you. Along with that, we have a graphical representation also. So this is the formula, okay, of the transmissibility. So just remember this formula. This is very important for you. First of all, a simple numerical can be asked. Now if you just plot a graph, here, just wait a minute, I don't have space so much here. Okay, so if I create a graph between the transmissibility okay, and the frequency ratio is omega by omega n. In that case, the graph is plotted something like that here. Sorry. So in this case, the graph is plotted something like that here. So here you can see, here we have transmissivity value equal to 1. Transmissivity value equal to 1, that simply means the forces which are being generated inside the machine, the unbalanced force which is being produced inside the machine is getting transmitted equally to the foundation here. Okay. And here we have a frequency ratio value equal to 1. That simply means the speed of the system is basically equal to the natural frequency of the system here. That means it is a condition of resonance here. Now here we have a value of the frequency ratio equal to √2. Okay, that simply means the speed of the system is basically higher than the natural frequency of the system here. So in this case, the graph is plotted like this one. So just remember the graph is very, very important for you. Okay, just remember the graph here. See the color of graph very carefully. Okay, see the colors of the graph very carefully. These are very, very important. So now you can see this red one is having a value of the damping coefficient as 0. This blue one is having a damping ratio of 0.2. It is having a value of damping ratio as zeta equal to 0.4, and yellow one is having a damping ratio of 0.6. Now what is the meaning of that? It simply means if the speed of the system is equal to the natural frequency of the system, at that point of time the value of the transmissibility is going to be more than 1. You can see, okay, these lines are representing that the transmissibility is having a value more than 1 here. That simply means if the 10 Newton force is basically acting on the machine, that in that case more than 10 Newton is going to be transmitted into the foundation here. That will be very, very dangerous for you. Okay, so, but now as you are increasing the damper, as you are increasing the damping coefficient, the corresponding damping ratio will increase and the value of the transmissibility will get reduced here. Okay, and correspondingly to ratio of the corresponding to frequency ratio value of √2, no matter whatever the value of the damping ratio or whether the damping is provided or not, the value of the transmissibility is always going to be equal to 1. Okay, so there is no use of damping here. Okay, so even though if you are using a damper, if you are not using a damper, it doesn't make any sense here. And if the value of the frequency ratio is more than √2, in that case you can see this red one is the bottom one graph is having a value of the damping factor as 0 here. So that simply means if the value of the frequency ratio is more than √2, in that case in order to have a transmissibility less than 1, in order to have a very low value of the transmissibility, the best option is to not to provide any vibrating isolating material here. Okay, so just remember that part. So as you are increasing the damping coefficient, the corresponding value of the transmissibility is increasing, and higher the value of the transmitted force are going to be there inside the system here. Okay, so I can say if the frequency ratio is greater than 0 and less than √2, greater than 0, this is having a 0 value, and √2. Okay, for all the value of the damping factor, the transmissibility is always greater than 1 here. You can see. Okay, so option number C is going to be the correct answer here. Just remember that part. So again a very simple question is here. Okay, now the next question is question number 12. The block has a kinetic energy. The block has a kinetic energy of 3 joule and a spring connecting the block has a potential energy of and elastic energy of 2 joule as shown in the figure. When the block is at x equal to 2 centimeter. So that means when the block has done the displacement, it is having a kinetic energy of 3 and it is having a elastic energy of 2 joule. But what will be the kinetic energy when the block is at x equal to 0? That is simply trying to say what is the value of the kinetic energy at its mean position basically. Okay, so if you remember, there is one method which is known as the Rayleigh method. According to the Rayleigh method, the energy of the system is always going to be conserved here. So I can say the kinetic energy is going to be maximum at its mean position. Okay, so whenever a system is vibrating, it is having a two type of energy. The first one is the kinetic energy and the second one is the potential energy. And at its extreme position, the potential energy will become maximum and the corresponding kinetic energy will become 0. And at its mean position, see, at extreme position, the potential energy is maximum, kinetic energy is 0. At its mean position, kinetic energy is maximum, potential energy is 0. Okay, but the total sum of the energy is going to be remain conserved. So I can say at x equal to 2 centimeter, the total energy is 3 joule plus 2 joule. And at the mean position, the total energy is going to be kinetic energy only. So we can say the kinetic energy of the system at x equal to 0 is going to be equal to 5 joule only. Okay, therefore the option D will be the Correct answer here. Next question. A machine of mass 100 kg is supported on 4 rubber pads at the 4 corners of the machine. Is found to have a maximum amplitude of vibration in the vertical direction at a frequency of 10 radian per second. Now, if the damping of the system is negligible, the stiffness of each rubber pad will be. Stiffness of each rubber pad you have to calculate now. Okay. So here we have a machine, and here I have installed a first spring, second spring, third spring, and fourth spring. Okay. So now I am assuming each spring is having a stiffness of K here, and it is having a mass of M here. Can I say that all the springs are in parallel connection? They are arranged in the parallel configuration here. So I can say the total spring, the total stiffness of the spring will be, equal to the simply a sum of all the stiffnesses here, that is K plus K plus K plus K, which is equal to 4K. Okay, and correspondingly if I calculate the value of the natural frequency, what will come? It will come to be as 4K by M. Okay, now what is given to us? We have been provided with the mass of 100 kg. We know the value of the frequency in radian per second as 10. So that's a very simple question. So just put all the values here. So I can say the answer is coming out to be as 10, 10, 100, 25. K is coming out to be 25 kilonewton per meter here. Okay, so option number, it is coming out to be 10 or 2.5? 10, 100 square 4K. Yeah, is units. Okay, okay. So it is coming out to be as K is equal to units. Check the units here. Kg. It is coming out to be as 10, 10, 100. 100 divided by 2. Under root of K is coming out to be as 50 Newton second per meter. Sorry, Newton per meter here. It is coming out to be that, and K is coming out to be as 25 Newton per meter. So I can say it is coming out to be as 2.5 kilonewton per meter there. Okay, so option number B is going to be the correct one. Okay, so just perform the calculation very well. Under root of 4K is equal to 2 root K. Okay, 2 root K. Now the next question. In this case, if you just see, a machine mounted on a single coil spring has a period of free vibration of T. If the spring is cut into 4 equal parts and placed in parallel and the machine is mounted on them, then the period of vibration of the new system will be. Okay, so let us say initially we have only one spring and here we have a mass. Okay, so if you calculate the value of time period, it will be equal to 1 upon F. It will be equal to 2 pi by omega n. Okay, so now in this case you can see what we have done. We have cut this spring into 4 equal parts. So always remember, so let us say here we have a spring. Okay, and if I cut this spring in 2 parts, let us say in the ratio of m ratio n, and the total stiffness is K, then the individual spring is having a stiffness of m plus n divided by m here. The second spring is going to have a stiffness of m plus n divided by n here. So in the same way, if I have cut this spring in 4 equal parts, 1, 2, 3, 4, 1, 1, 1, 1. Okay, so now you can see the individual spring are going to have a stiffness of 1 plus 1 plus 1 plus 1 plus 1 divided by 1 here. The new stiffness will become equal to 4K. If the initial stiffness is K, then the new stiffness of each spring is going to be equal to 4K. Now what we have done, we have placed them in parallel. So that simply means now we have 4 spring like this one, and each spring is having a stiffness of 4K here. Okay, so I can say the natural frequency will become equal to 16K by M here. which will be equal to root 4k by m. Okay, so here you can see, so I can say the initial natural frequency of this system is how much? Omega n. It will be equal to root k by m only. So therefore I can write omega n dash is equal to 4 times of omega n. So therefore the new time period will become 2 pi by omega n dash. It will become 2 pi by 4 omega n, and 2 pi by 4 omega n will be equal to T upon 4 here. Okay, so I can say due to the increased stiffness of the spring, the time period has been reduced by a factor of 4 here. So option B will be the correct one. That will be the answer here. Okay, now the next question. A spring mass system is shown in the figure. A spring mass system is shown in the figure is actuated by a load of P equal to 0.75 sin 2t. If the mass of the block is 0.25 kg and the stiffness of the spring is 4 Newton per meter, the displacement of the block will be. Okay, so now just see, this question is from the force vibration case and it is acted upon by the variable force with a frequency of 2 here. Okay, in this case the frequency of the force is 2 here. Now in this case, what do you want to ask? You want to calculate the value of the displacement here. Displacement simply means amplitude. So amplitude is having a formula. Just remember the formula. Formula is very, very important for you. It is having a formula of F naught by K 1 by omega n square plus over square 2 zeta omega by omega n whole of square. That is the formula of the amplitude here. Okay, so just put all the values here. So F naught is given to us, that is 0.75. Okay, stiffness is given to you. How much stiffness is there? Stiffness is given to us 4 Newton per meter, and correspondingly there is no damper. So I can say zeta is going to be 0. Okay, and this will become 1 minus omega is 2, and what is the value of omega n? Omega n is root k by m. K is 4, m is 0.25. So I can say omega n will become 4 here. So I can say it will be equal to 2 by 4 square. It will come out to be as 0.75 divided by 4 multiply by 1 by 0.25, 0.75 here. Okay, so if you simplify it, the answer will come out to be as 0.25. Okay, this will be the amplitude here. So option number A will be the correct answer. So again, a question is very simple here. Next question. Choose the correct option for the given blank space. While using the dash method to find the natural frequency of the vibration, it is assumed that the kinetic energy at its mean position is equal to the potential energy at its extreme position. I have already explained you this. So basically this is according to the Rayleigh's method here. Okay, so option number D is the correct one here. Okay, so kinetic energy at its mean position is going to be equal to the potential energy at its extreme position, or I can say the sum of the potential and kinetic energy at any random position. Okay, that is a conservation of energy part. Next question. Which of the following gives the expression for the magnification factor at resonance in the force vibrating system here? Okay, now here comes the topic of the magnification factor here. Now what is the magnification factor? So basically the magnification factor is defined as the ratio of the amplitude of the steady state response. The ratio of the amplitude of the steady state response. To the static deflection here. Just remember that part. So just right now we have seen the displacement. In the last question we have calculated the value of displacement. Okay, here in this case you can see. So this is representing the amplitude, okay, when the system is acted upon by the force here. So that is the amplitude of the steady state response. Now if I just divide the amplitude of the steady state response with the static deflection. Now what is the meaning of static deflection? If the mass is acted upon by a constant force, in that case the static deflection will become force divided by stiffness only. Okay, if the force is acting continuously with a constant magnitude, in that case the displacement is going to be equal to F by K only. Okay, so if I simplify it further, you are going to get the magnification formula as 1 minus omega by omega n whole of square plus 2 zeta omega by omega n whole of square. Okay, so you can see here resonance condition is told here. So I can say at resonance the omega is going to be equal to omega n and the frequency ratio will become equal to 1 only. Therefore the first term will become equal to 0. Okay, and this omega will cancel out. Therefore the magnification factor will become equal to 1 upon 2 zeta here. Okay, that is the case. So I can say it will be equal to 2 zeta. Okay, now the answer is given in the form of damping coefficient, natural frequency as well as the stiffness here. Now what is the formula of the this damping factor? We know, the value of the damping factor, we know it is equal to C by m multiplied by 2 omega n. That is the formula. So just put this value here. You are going to get 1 upon 2 C upon 2 m into omega n. So 2 will cancel out. It will come out to be as m omega n by C here. Okay. So in this case, do we have any options in this form? Okay, the answer is not given in this form here also now. So we have to write it down in some other form. Okay, so we have to write it down in some other form also. So just simplify it further. So we have to simplify it further. So let us say just multiplied by the S by m here, multiplied by S by m and just divided by the S by m here. So here you will find there is no change in equation. So I can write m multiplied by omega n divided by C. It will become S by m only. Here it will become 1 upon omega n square. Okay, so m will be cancel out and omega n will be cancel out. So option will become S upon C multiplied by omega n. So formula can be written, can be rewrite in this way also. So S upon C omega n. So option number A will be the correct one here. Okay. Next question. Find out the correct free body diagram for the middle mass. For the middle mass here, for the given spring mass system in the figure below. So now just if you observe very carefully, the given mass is basically connected with two other masses here, and in between we have three different springs, which is having a stiffness of K, 2K, K here. Okay. Now this mass is having a displacement of x3. This mass is having a displacement of x3. Middle mass is having a displacement of x2 in toward right, and the first mass is having a displacement of x1 toward right here. Now what will be the free body diagram? So just understand. Here we have 2m mass. Okay. Now you can see x3 is the displacement due to this particular mass here. Okay, and x2 is the displacement due to this middle mass here. So I can say the resultant displacement of this 2m mass is going to be equal to stiffness, this stiffness multiplied by the difference between the displacement here. This will be the net force which is acting over the middle mass here toward right here. In the same way, I can see here we have spring of stiffness 2K. Now the middle mass is having a displacement of x2, correspondingly the first mass is having a displacement of x1 here. So I can say the net displacement of this particular spring is going to be equal to 2K x2 minus x1 here. Okay, so this will be the net forces which is acting over the middle mass here. So I can say the option number 2K x2 minus x1 K x3. Option number B will be the correct one here. Okay, So again, it's a very simple question. You just have to create the free body diagram by considering the net displacement of the springs here. Now the next question. According to the Dunkersley empirical equation, the frequency of the transverse vibration of the system of several bodies attached to the same shaft. So that's a very simple question. In this case, you have to remember the exact formula here. Basically, it is basically used for the transverse vibrational case here. Okay, to calculate the value of the natural frequency of the entire system. Now the next question, last question of this particular series. A shaft of 50 millimeter diameter and 1 meter in length carries a disc which has a mass eccentricity equal to 190 microns here. The displacement of the shaft at a speed which is 90% of its critical speed. Okay, so now you can see the speed of the shaft, that is omega, is 90% of the critical speed. And what is critical speed? Critical speed is equal to the natural frequency only. So I can say omega by omega n is going to be equal to 0.9 here. The frequency ratio is 0.9 here. Now what do you want to find out? The displacement of the shaft. So now just see, in this case we have a direct formula for calculating the value of the displacement, and that formula is written as equal to y equal to eccentricity divided by omega n by omega square minus 1. That is a direct formula which we have to use. So in this case I can say eccentricity is given to you 190 microns. Omega n by omega n is 0.9, so it will be 1 upon 0.9 square minus 1. Okay, so this will be the equation here. So if you just solve it, you are going to get the value of the y as 8110 microns here, which will be equivalent. Okay, it is given in the option here now. It will be equal to option number A here. So that's again a very simple question here. Understood? So here you can see this chapter is very, very simple here. The only thing is you have to cover up these basic parts. You have to just see some formulas here. You don't have to do the entire mathematical derivations of this particular topic here. Understood? So so that's it for this particular video. So I hope you like this particular video here. Okay, so you can also just go through the practice questions like this one from your books itself, and we have already shared the practice PDF with you also. Okay, you can go through that PDF also. In that case, you are going to in those PDFs you are going to see the lot of questions like this one only. Okay, so thank you very much.